Okay, so today we'll start our session. So today also uh, there is no attendee. Still, I will be recording today's session for future reference. But yes, I would suggest please try to join this session for better understanding of each and every questions, whatever is going through the weeks. So let's start today's sessions. So the first question asks to match the followings. There are four different types of weldings, and with them, which would be matched in regard to different kinds of welding. So there are different kinds of welding such as gas tungsten arc welding, submerged arc welding, gas welding, electron beam welding, and there are four different items are there like vacuum chamber, chemical heat source, non-consumable electrode, and consumable electrode. Now, if you see in gas tungsten arc welding, in gas tungsten arc welding, basically the arc is maintained between a non-consumable tungsten electrode and the workpiece in a protective inert gas atmosphere. Uh, so any kind of filler material needed is supplied externally. So in gas tungsten arc welding, normally a DC arc is used with tungsten as the negative pole. This is not possible for metals such as aluminium and magnesium, where the oxide layers persist if the workpiece is used as the anode. So yeah, for gas tungsten arc welding, we generally use non-consumable electrode. So yeah, so in gas tungsten arc welding, it will be a non-consumable electrode. And if we see in submerged arc welding, the arc is maintained underneath a mass of fusible and granular flux. So the process, first the flux, it basically contains kind of calcium oxide, calcium fluoride, silica that is sintered to form a coarse powder. This granulated flux is then sprayed over the joint to be made. And so in submerged arc welding, basically it is consumable electrode. Now in gas welding, it will be a chemical heat source. So in gas welding, there will be no voltage current characteristics of power source. It will be purely of supply of gas of oxyacid, oxygen, and acetylene. And because of mixture of oxygen and acetylene, you will have some flame called oxyacetylene flame, through which you apply the heat flux over the workpiece, and you melt the workpiece and develop some weld pool over the surface. And for electron beam welding, if we see in electron beam welding, the heat for fusion is obtained from the kinetic energy of a dense beam of high velocity of electrons. So in general, the entire operation is carried out in vacuum, maybe with a pressure of something like 10 to the power minus 3 mm of Hg. So yeah, in electron beam welding, it will be operated in vacuum chamber. Now in question 2, it also asks to match the followings. Uh, there are different kinds of welding like electro slag welding. There is something called gas cutting. There is something called FSW, and also something called plasma spraying. Now If we see something about electroslag welding, so in electroslag welding process, it's particularly suitable for welding of thick plates. So in electroslag welding, this will be particularly used for thick plates. So initially the plates to be welded are set up vertically, maybe with a gap of about something kind of 2 to 3 centimeter, and also the filler wires and plugs are kept in that gap. Here the filler wires are used as the electrode. So yeah, in electroslag welding, this is specifically used for thick plates. Now, if you see gas cutting, uh, as I said, in gas welding, you use something called oxyacetylene flame. Now, in oxyacetylene flame, it will be three different kinds. One is neutral flame, one is carburizing flame, and one is oxidizing flame. Basically, in neutral flame, your uh, the ratio of two gases will be 1:1. In carburizing flame, carbon amount will be higher, and for oxidizing flame, amount of O2 will be higher. So always whenever there will be high amount of oxygen, there will be high amount of temperature, and it is generally used for something called cutting operation. Now for FSW operation, we all know that this is a solid state kind of welding. So in if we rub it, I discussed it earlier also, in FSW you'll have something called tool, and it rotates and plunges over the workpiece, and this happens mostly something at zero point 0.5 or zero point 0.6 of the melting temperature of the base material. So whatever pressure and temperature generation happens, that happens because of the rubbing of the tool over the workpiece, and some solid state deformation happens of the workpiece, and joining happens at solid state itself. It doesn't go to that melting region. So yeah, for FSW it will be a solid state welding. Gas cutting is for oxidizing flame, and now for plasma spraying and coating, it will be obviously non-transfer. So in plasma arc welding, there are two different kinds of arc. One is transferred arc and one is non-transferred arc. In transferred arc, the electric arc is basically established between electrode and the workpiece. It can produce stronger kind of weld than non-transferred arc, because molten metal from the workpiece reinforces the weld beam, right? So monitoring of the welding is very easy here. But in case of non-transfer arc welding, the arc is established between the electrode and the constricting nozzle of the plasma torch. In this type of welding, the heat of the arc melts only the wear electrode, only the electrode portion. The molten metal from the electrode forms a pool over the workpiece surface. So for plasma spraying and coating, it will be a non-transferred arc. Now, if you see question 3, it asks about something from resistance welding. So it says in a resistance micro welding process, the applied voltage is 5 volt. The overall contact resistance between butt joint sheets is 5 into 10 to the minus 4 ohm centimeter square. And when it asks about what is the amount of generated heat per unit area during the process. So here voltage is given as 5 volt. uh, Overall contact resistance between butt joint sheets. Overall contact resistance is given as ohm semi square. So we need to find out the amount of generated heat per unit area during the process. So we know that the generated heat can be described in terms of Q equal to I square RT, where I is the amount of current transferred into the workpiece, R is the resistance, T is the amount of time of the welding. So from here we can find out, and yeah, if we explain V and I relationship from this, then the amount of heat transferred will be derived from this equation. So here V is given, R is given, and you need to find out heat generated per unit area. So if we think of it as per unit time also, so your V is 5. The unit will be in terms of watt per centimeter square. So this is basically heat generated per unit area per unit time. Now this will be what? 5 into 5, like 5 into 10 to the minus 4. So this will be simply 5 into 10 to the power 4 watt per centimeter square. Let's move to the next question. So the next question tells that the voltage length characteristics of a DC arc is given by V is equal to 20 plus 40L. So it gives some relationship of voltage and arc length in terms of some linear relationship, uh, where I is the where L is the length of the arc in centimeter. Now your power source characteristics is approximated by a straight line with a function of this. So your power source characteristic is given as, so this gives you a relationship between voltage and current. So from this relationship we can figure out what is the voltage. So voltage would be this, and your voltage and length characteristic is given by V is equal to 20 plus 40L. So we have two equation of voltage which will be similar for same operation. Now, what you need to determine? You need to determine the optimum arc length and the corresponding arc power. So somehow we need to calculate the power in terms of length, right? So if we equate these two voltages, if we equate these two voltages, from here what we can find out? We can find out some relationship between length and I. So your I will be how much? So your I will be 20 plus 40L Let's do step by step. 1 minus I by 1000 into 20 plus 40L by 80 I by 1000 is equal to 1 minus 20 plus 40L by 80. Now my I is coming as 60 minus 40L, that into 1000 by 80 amp. Let me move these things. Now if our I is given as this, and we know power is V into I, your V is given as 20 plus 40 into L, and I is given as 60 minus 40 into L. So now we need to find out, determine the optimum arc length and corresponding arc power. So for optimum arc length, it will be simply dPdL will be equal to 0. And if we do some derivative here for this, 40 into 60 minus 40L minus 40 into 20 plus 40L. So from here we can simply find out the L value. For me, this is coming as 0.5 centimeter. I will urge you to please try to match the answer. And if your arc length is coming as 0.5 centimeter, so from there you can simply find out the optimum power as 20 plus 40L. 40 is 0.5, so by 2, that into 60 minus 40 by 2, that into 1000 by 80. Okay, I hope for this question you got the concept, and if there is any confusion, maybe you can mail me. Okay, maybe you can mail me through this mail ID. I will try to resolve if there is any confusion. So let's move to the next question. This is also from resistance spot welding operation. So in question 5, it says that a resistance spot welding operation is used to join two austenitic stainless steel thin sheets. Here we assume here we assume complete melting of the sheets, and considering formation of cylindrical shaped nugget, we need to evaluate the portion of heat generated used to form the nugget, and some process conditions are given here. So in this question, what are given? The given the given conditions are sheet thickness is given, which is 2 mm. Nugget dia is given as 6 mm. We have the welding time as 0.15 second, and yes, The good thing is given as energy required for melting is given 35 joule per mm square. So I simply know that Q is equal to I square RT, right? And from here, if we somehow find out the total heat flux from this, and okay, we need to find out what we need to find out, evaluate the portion of heat generated used to form the nugget. Acha. So it will be something like this. What will be the portion of heat that will be used? So some amount of heat will be required to melt the workpiece, and there will be total heat, right? So heat generated during welding. Now, if we try to find out what will be the heat required during melting, so it says that energy required for melting is 35 joule per mm square. So what will be the total heat required for melting? It will be 35. Sorry, this would be per unit volume. It will be 35 to pi by 4 into 6 square. That is your area, and your sheet thickness is coming as 2 mm. So this amount is your total volume of the material which need to be welded, and that into your energy required for melting is 35 joule per millimeter cube. So this will be my sheet required to melt the workpiece. And what will be the heat generated during welding? So we have the current here, we have the resistance here. Oh, and we have the time also. So it will be 15,000 square. So 15 kilo ampere is 15,000 ampere. That into 0.0002 ohm. That into my time. This much of joule. So the fraction of heat which will be used is, so the fraction of heat which will be used is 35 into pi by 4 into 6 square into 2, that divided by this into 0.0002 to 0.15. I do not have the calculator now, but I hope you got the idea how to figure out what will be the portion of heat generated used to form the nugget. Now moving to next question. Uh, moving to next question. This asks that an experimental investigation reveals that the optimum heat input for joining of 1 mm thin steel sheet by gas tungsten arc welding process lies between 40 to 80 joule per mm. So for gas tungsten arc welding process, this value is given, which is the optimum heat input for joining of uh, this this thin steel sheet of 1 mm thick, and now an operator conducts experiments to join the same steel sheet under following weld conditions. So the conditions are given here. Now we need to find out that whether the condition are suitable to join the sheets. So basically from these given conditions, we need to find out the what will be the heat input, and we need to verify that that value is coming in between 40 to 80, or this is something less than that or greater than that. If it is less than that, then it is not suitable. If it is greater than that, this then the heat generated is will be so high that melting will be in higher amount in that workpiece, right? Now what will be the heat input for this given condition? You have the voltage, you have the current, and you have arc efficiency. So if you see amount of heat which is actually going into the workpiece is V into I into the efficiency. So your voltage is given as 10, current is given as 25 ampere, and efficiency is given as 0.7. So it's coming as 135 volt ampere. Now we have the welding speed as we have the welding speed as 6 mm per second. So what will be the heat input per unit length? So your power is coming in terms of watt, right? That is joule per second. And you have your welding speed. And if you need the heat input per unit length, you need to simply divide the total amount of heat flux that divided the velocity. This is joule per mm. How much this is coming as? 22.5. So if this is 22.5 joule per mm, and for experimental investigation which has been revealed that optimum heat input for joining this thin steel sheet that lies between 40 to 80 joule per mm. So obviously these process conditions are not suitable to join the sheets. Okay. Now let's move to the next question. this question is from again from welding operation, of course. Uh, this says that during a TIG welding process, arc current and arc voltage, these are given. So your arc current and arc voltage is given as 50 ampere and 60 volt respectively. And it says that when the welding speed was 150 per minute. So your there are two cases. One is arc voltage where 50 ampere and 60 volt when your welding speed was 150 per minute. And in another process, the welding speed was 120 per minute at the same arc welding voltage and heat input to the material so that the weld quality remains the same. So we need to determine the welding current for this process. So in the earlier question, we find out that heat input per unit length is simply what? Power divided by the velocity. So voltage into current that divided the velocity. Now it says that heat input to the material remains same so that the weld quality will be same. So if the heat input will be same, it will be simply what? V1 I1 by V1 equal to V2 I2 by V2. Here we are assuming that initially it was in the earlier question there was some arc efficiency given. Here we are assuming that 100% it is 100% efficient, but of course in reality it is not that way. So let us ignore the efficiency part. So if this is true, for case 1 your voltage is given as 60 volt, I1 is given as 50 ampere, and velocity 1 is given as, this is my case 1. It is case 2. For case 2, it says the same arc welding voltage. So V2 is again 60 volt. You need to find out what is current, and our velocity is given as 120 per minute. Now if this equation holds true, it will be simply 60 into 50 divided by, if we convert it in terms of per second, that will be equal to 60 into I2 divided by 120, this. So 50 into 60 divided by 150, I2 into 60 divided by 120. So my I2 is coming as 40 ampere. Okay.
Yes, sir.
Okay. There are two questions more. What is there in question 8? It asks that two pipes of inner die of 100 and outer die of 110 Each are joined by butt welding using 30-volt power supply. So what values are given? Let us compile that first. Sorry. Inner die is given as 100 mm. Outer die is given as 110 mm. Voltage is 30 volt. It says that at the interface 1 mm of material melts from each pipe, which has a resistance of 42.4 ohm. So R value is given as 42.4 ohm. Your unit melt energy is given as 64.6 days. So if this is given, we can find out the total amount of heat which is coming at the workpiece. This will be the given value that into the volume. Now what is the volume? The volume is like this. Okay, let's find out the volume separately. So our inner die and outer die is given. So area will be simply this, and that will be some thickness, that into some thickness. So it says that at the interface 1 mm of material melts from each pipe, and then you have two pipes, so it will be simply 2 mm, right? And your melt energy is given in terms of per meter cube. So if this is millimeter, okay, so total energy input be equal to 64.6 into this into 2, that into 10 to minus 9, that is in megajoule. Now if we have the total energy input, and again we know that Q is equal to I square RT, and V is sorry, V is equal to IR. So simply Q will be, okay, we need to find out the time required for melting. Now if I square at I is equal to V by I, it will be simply Q by V square by R. Okay. So V value is given as 30 volt. Resistance is also given. We have find out the total energy input as this. Okay. Now everything is given. So time will be coming as this is second. I don't know what will be this answer. If this is say X megajoule, maybe we can find out in terms of X joule. So X into if resistance is 42.4 divided by 30 square, right? Okay. Okay.
Yes, sir.
2 pi. Yeah. Okay. So let's move to the last question for today's session. Says that spot welding of two 1 mm thick sheets of steel for which the material property is given in terms of density is carried out successfully by passing a certain amount of current for time is given again. So all the concepts are revolving around this equation only. So that should not be too tough to understand. You have the time given as 0.1 second, and what is given is resultant welt nugget formed is of 5 mm dia, d is 5 mm, and thickness is, so now I am given the notation of thickness as z because the time is t. Z is 1.5 mm, and your latent heat of fusion. So it's basically the total heat input, not the total. This is per kg. It is given as 1400 kilojoule per kg. So if you want to find out the total heat flux which is coming, that will be equal to Q into the mass of whatever uh, the steel plate is having. So if this is 1400 kilojoule, mass is your rho into volume, and now let us determine it at separately. Your rho into volume is equal to, this is given as 8000 kg per meter cube. G is given as 5, Z is 1.5. So volume will be, this is in millimeter cube. That will be in meter cube. So 8,000 into 5 by 4 into 5 square into 1.5. That into 10 to the power minus 9. This is your mass of the system. Am I right? So total heat flux will be what? 1400 into 8,000 into 5 by 4 into 5 square into 1.5 into 10 to the power minus 9. That will be in kilojoule. Let's say this is something you need to find out, of course. Let's say this is x. After converting in terms of joule, let's say this is x joule. And now you know that Q is equal to I square RT. What you need to determine here? Okay, you need to determine the current. So I square will be Q by RT. You need the Q as X joule. I mean, if your Q is X joule, what your R value is given as is 200 micro ohm, and your T value is given as 0.1 ampere. Okay, okay. So I hope you are well understood the concepts, and you have any problem, please let me know, and you can mail me also. If there is any confusion, you can ask me now, or you can end today's session here. Okay, so let's end today's session here. Have a good day. Bye bye.